Okay, so this problem reads, a light rail commuter train accelerates at a rate of 1.35 meters per second squared. How long does it take to reach its top speed of 80 kilometers per hour starting from rest? So this is part A of this problem. We have 3 parts to the problem. So the first thing we want to identify is what is our object of interest, and that is the train. So we're interested in looking at the motion of that train. So what is our initial condition? When do we start carrying? And when do we stop carrying? Well, the train is going to start from rest and accelerate to its top speed. So we start carrying when it starts accelerating. All right. And when do we stop carrying? When it reaches its top speed. So that is where we're going to frame this problem. Okay, so here's our train, and we'll say it starts at our origin, position equal to 0. So x initial, x final, v initial, v final, acceleration, and time. Well, our initial position is 0. Problem doesn't tell us the final position, so we don't know that. It says it starts from rest, so our initial velocity is 0 meters per second. We know that it reaches its top speed, which is 80 kilometers per hour, so we right away recognize I'm going to have a unit issue that we're going to have to take care of. It tells us that it accelerates at 1.35 meters per second squared, and we don't know the time. So we're interested in determining how long that takes. We're interested in this time. Which equation do we use? Well, I don't have final position. So my final position equation may not be helpful to me, but I do have initial and final velocity. So I can use this relationship. But we want to recognize that we have to be in the same units, and we see that our velocities and our accelerations are not in the same unit. So let's convert our velocity to meters per second so that we can be in the same unit as acceleration. So 80 kilometers per hour, and I want meters per second. Well, I know if kilometers is on the top and I want meters on the top, I need meters on the top, kilometers on the bottom. I know there are 1,000 meters in 1 kilometer. Similarly, I have hours on the bottom. I want seconds on the bottom. Give myself a little more space. So I'm going to put hours on the top and seconds on the bottom. I know in 1 hour, there are 3,600 seconds. So 80 times 1,000 divided by 3,600. And we end up with 22.2 meters per second. So 80 kilometers per hour is 22.2 meters per second. And now I'm in my right units. All right, so V final, 22.2 meters per second. Oh, I don't need that meters per second in there. It's going to just get messy with my units. Is equal to V initial of 0 plus an acceleration of 1.35 times time. So that 22.2 divided by 1.35, and we get a time for that acceleration phase, speeding up phase, of 16.5 seconds. All right, so this is part A. Perfect. Now, part B tells us that that same train decelerates, slows down at a rate of 1.65 meters per second. So how long does it take to come to a stop? Well, this is a different problem with 2 different initial and final conditions. I'm going to leave this up here. Same object, but in this case, the initial is when it starts to slow down. And the final is when it comes to a stop. All right, so let's say it's starting, we're going to change our origin back to that when it starts to slow down. It's way down the track from where we were, but we're just sort of interested in how long it takes. So we're starting this problem over. We can identify a new origin. So x initial, x final, v initial, v final, acceleration, and time. I'm going to say the train is heading to the right. So it starts at 0. Not sure where it ends. Our initial velocity is that top speed, the 80 kilometers per hour or 22.2 meters per second. It's going to come to a stop of 0 meters per second. And it says it's slowing down at a rate of 1.65 meters per second squared. Now, if it's moving to the right and slowing down, that means the direction of the motion and the direction of acceleration are opposite. Slowing down, they're opposite. So that acceleration must be negative. And we don't know the time. All right, so we're interested in how long it takes for that train to come to a stop. So we're interested in that time. And again, we have our initial and final velocity. So we can use the velocity relationship to solve for our time. So v final is 0. V initial is 22.2. My acceleration is minus 1.65 times our time t. So I bring 22 over. I have minus 22.2 is equal to minus 1.65 times time. And 22.2 divided by 1.65 gives us a time of 13.5 seconds. Now, should that time be lower, faster, lower number than the speed up? Yeah, because they can brake at a higher acceleration than they can speed up. Okay, now part 3 says in an emergency, the train can actually slow down more rapidly, coming to rest from 8 kilometers per hour to rest in 8.3 seconds. So what acceleration can it achieve in that situation? Well, that condition is similar to this one. So I'm going to use this side of the board to erase our situation. I'm just going to erase our list for that scenario because we have a slightly different situation in the problem we're being asked for. All right, so in this case it says that it goes from rest to a stop, but it's happening a little bit faster. It tells us it can do that in 8.2 seconds. So how does our list change if that's the case? So this is problem number 3 in this question. Ooh, lots of shaking. So our initial position, we can still use that as 0. We don't know the final. It tells us it's starting at its top speed. Again, that's 22.2 meters per second, and it's coming to a rest, 0 meters per second. We don't know the acceleration of this particular situation, but we do know it happens in 8.30 seconds. So we want to know, what is the acceleration? How quickly does it slow down? And your problem uses the word deceleration, telling you it's slowing down. So we're interested in that acceleration. And again, I know my velocity, so we can utilize this relationship since I know my two velocities. V final is 0. V initial is 22.2 plus my acceleration. And in this case, I know my time. Can bring my 22.2 over to the other side, and I get acceleration times that 8.3. So we have negative 22.2 divided by 8.3, and we get an acceleration of negative 2.67 meters per second squared. Now, we know negative is appropriate because it's moving to the right, positive velocity, and slowing down. Slowing down says they're opposite. It must be a negative acceleration. All right, so 3 parts to that problem, all sort of utilizing this idea of an accelerating object Recognizing when that acceleration needs to be positive or negative, again, relating it to the direction of motion, and whether it's speeding up or slowing down. Good job.